Hello, and thank you for joining us. Today's presentation is Tips and Tricks for Low Level TOC Analysis. Our presenter is Tyler Trent, our Elemental Product Marketing Manager. We will be taking questions, so feel free to submit them throughout the presentation, and we will address them at the end. This webinar is being recorded and will be available within a few days. Okay, now I'm going to turn it over to our presenter, Tyler Trent.
So thanks, Shelley, for the introduction. So here today, we're going to be talking about some tips and tricks for low-level analysis on the Fusion TOC system that we have here at Teledyne Tekmar. So a little bit about what we're going to be talking about today is we're going to go over some background information, what you should know before you start, how do we optimize methods, calibration, sequences, and other parameters within the system. And then we're going to go over some real-world results and have some discussion about that. So first, background. We're going to talk a little bit about this, and this might be very introductory, but we're going to make sure we understand some terms first before we go and get a little bit further into low-level analysis. So one thing that we need to understand is really what an LOD versus an LOQ is. So limit of detection. Well, that's really the lowest concentration level that can be determined statistically different from a blank. A lot of manufacturers, we like to put our LODs onto our manuals or into our brochures and state that as a specification. But one thing that we also do is we need to look at the limit of quantification. What can we actually measure with a certain degree of certainty? So that's going to be our LOQ. So for this presentation, we're really going to be focusing more on the LOQ aspect. What can we see? How can we quantify it? And how do we get our best results down at that low level? So the purpose of this webinar is we're going to demonstrate the lowest level of TOC achievable in the Fusion with accuracy and precision with accordance to the LOQ. When we start looking at the accuracy or precision in this study, we define it by certain parameters. 10% of the actual value within the check standard, and the precision means 5% RSD in triplicates. So for this study, we held all of our sampling to that type of scrutiny. So where do we need low-level analysis at? Where do we need to see this, or what does it need to be employed at in the field? Well, the first realm is going to be pharmaceutical. Pharmaceutical is very key. Why is that, you ask? Well, certain methodologies out there, such as water for injection. Water for injection can contain no more than 50 ppb of carbon. Clean in place, CIP, or swabs, basically, we need to be able to measure low levels of contamination. So it's very key for us to have very clear, good, and precise analytical results at a low level. And that's one thing that we see with the Fusion in the pharmaceutical realm. Also in the food and beverage, cosmetics, and semiconductors, it is very key also for low-level analysis. So why is UV persulfate better for low-level analysis compared to some other techniques out there, such as combustion or other types of detection capabilities, such as membrane conductivity? Well, you're going to get a little bit more accurate results, and you're going to have less background from combustion. So it's going to be more sensitive. So the reasons that we kind of choose UV persulfate system is the matrix that contains salts, azides, nitrates will also result of membrane conductivities. They will have some interferences and could be clogged, and the analytical results could become unreliable. Combustion, as you know, we also sell the Lodex and Torch, but with combustion, we won't be able to get down to the low level of 50 ppb that is needed because of combustion is a little bit more of a dirtier technique. So with UV persulfate, we can reach those low levels. So let's talk about some tricks and tips before we get started here. So this might fit in for some drinking water analysis, but this is typically going to be for low-level analysis when we're talking about less than 1 ppm. So organic carbon is everywhere. Air by volume is 0.04% CO2. So one thing that we have here is a closed system. Our closed system doesn't allow for any outside air to get in other than the sample gas we are using. And then also, one bacteria on your hand can grow into a million. Bacteria is carbon. Bacteria is a living organism. So shelf life of the sample. How long do samples live in the vials? Can they be contaminated from outside sources? How do we set our lids? Do we set our lids with the cap up, with the inside up, or down so it doesn't obtain mercury? Or sorry, TOC, carbon. So knowing some stuff of where carbon is in the laboratory is kind of important. And this some of this stuff could contribute to a larger value. So with that said, what I mean a larger value is it could fluctuate our LOQ or an LOD because of outside interferences or outside carbon. So we want to take special care when we're working down that low level. So we're going to suggest some type of purity and expiration for certain types of chemicals. So your starting materials are very important to low-level analysis. This is the minimum specs on the screen that we kind of suggest for low-level analysis. Some things to consider when setting up the fusion and buying reagents. So obviously we need ultra-pure gas, reagent water, ASTM type 2, less than 50 ppb of carbon. Especially when we're working in the pharmaceutical realm, our reagent water, according to USP 643, should be less than 100 ppb. So we can also actually get certified water that needs to be replaced daily. Vials, certified vials to be less than 10 ppb of carbon contributing, and you shouldn't reuse vials, so you need to put new vials for each sample every day. Reagents such as your persulfates, your acids should be a high technical grade, ACS grade. And those should be replaced according to your SOP, but sometimes we suggest replacing every start of the week. And then system cleanliness. When we go through and look at how our system is cleaned, we want to make sure that on our last total carbon rep for our system clean, we're less than 3 ABSs to ensure the system is going to work properly at those low levels for us. So it's suggested in the manual to allow 30 minutes for the lamp to warm up and get to full UV oxidation, to get to in a ready state, in a ready mode for sampling. This will help your sensitivity. We don't want to expect anyone to stand there for 30 minutes with their busy schedules. So what we can do is we can put a couple cleans at the very beginning of the schedule that's going to clean the system up while the lamp is warming up. So that helps with a little bit of a productivity there. But we recommend the UV lamp to warm up for at least 30 minutes before running your analytical samples. So from this screen, I'm talking about a clean. Well, what is a clean? So on the fusion system, we can actually go through and do a little bit of cleaning. So first, a little bit about how the cleaning procedure works. The system takes a volume of DI water and is pulled into the reservoir, and it is cycled back and forth between IC Sparger and the UV reactor 3 times. Once for the TC rep, every time the water cycles through, it analyzes carbon content and the absorbance counts related to the report that's going to be shown on the screen. The process actually purifies the water used, which is why the count should get lower. So the first TC clean rep results represent carbon present in the water plus carbon present in the sample pathway. A typical result here is anywhere between 10 to 15 ABSs, absorbance from ultra pure water from the clean reservoir. This is what we're trying to target for low-level analysis to make sure that we're hitting less than 5 or less than 3 on this last rep. So a result for the TC clean that is greater than 20 ABSs should be of a concern. It should be a warning sign to the analyst or to the system operator. It can be indications that the system or the water is contaminated with bacteria, or you have some other type of outside contamination occurring. So not only clean the system, but it actually reports that the system's clean to you. It actually tells us how our fusion system is doing. So when we look at here, so we have an example of a good clean and a bad clean. So the first up top is actually a good clean. We see the first IC rep gives us a certain value of less than 3 ABSs. Then our first TC clean is less than 15 ABSs. It's in the third column. Then as we continue to go back and forth with that water, we see it continuously drop and drop and drop. That's what we want to see. We want to see our last rep on our TC clean below that 3 to 5 level, ABS level. So what do you mean if we have a bad clean? Or what do we have if the system is contaminated by an outside source, or the source water might be contaminated also? Well, we'll see the TC cleans not really change over time. So as we can see for the bad one below, the first rep should be less than 15, but it's actually doubled at 32. And it should continue to clean up over time, but it doesn't. As the reps continue, we see it doesn't change. So we know we have some type of system contamination, that our system is not cleaning up properly, so we can check a few different things. Our source water, our water in our reservoir, or we might need to go through and do an acid wash on some of our glassware components, which is a very common maintenance item that we have to do from time to time. So there's different types of contamination. So if you see a really high TC clean on the very first one, but it continues to go down, clean or replace the DI water in the reservoir, replace tubing from the DI water container, or maybe if you might have some particulates or other items that can't be rinsed out, you might have to replace a certain valve or a port, 7-port valve. So the top is an example is what it looks like if your reagent water is not clean enough. It will start out high, and then of greater than 15 on the ABSs for the first TC rep, but by the third rep, it will start to look normal. So that's something we need to keep into consideration. Now, when we start looking at the other system, well, down below, kind of like what I said, where it's not cleaning up, is we're going to have to run additional cleans to see if that does clean up the system. Maybe we need to clean the glassware, or even we might need to run some acid through the system to help clean it up in different spots in different locations. The last one, running acid through the sample system, is more extreme. Most laboratories will never have to do something like that, but there's one case out of so many that you might have to do that. And it actually cleans the tubing and pathway a little bit better, a little bit more aggressively, to get these cleans into a better level, so the system is manageable to run at low ppb levels. So tips for blanks. So when we want to look at a blank, so once we have a good clean system, we want to blank the system. We want to understand what a blank is. Notice the cleaning procedure is automatically included in the blank procedure. This is done for a purpose by purifying the water before reagents are injected, so displaces any DI water issues. So for this, 3 milliliters of persulfate is injected into the purified water and analyzed. This is reported as the reagent blank. It should be less than 15 ABSs, which is the 5 ABS counts per 1 mil. So we kind of look at how much are we contributing per 1 mil of our reagents or blanks for calculation purposes. If greater than 15 adsorbents, this means your sodium persulfate solution may not be pure enough for low-level analysis. So that comes back into consideration of ACS grade material, material that's going to be more pure for this type of analysis and doesn't provide any background contamination. So after the reagent blank is measured, we're going to have an acid blank. So 1 milliliter of the phosphoric acid is injected to measure its carbon contribution. The acid blank should be less than 3 ABSs per mil. So as we see here, we're getting pretty good values for our acid in our reagent blank, all below the values that we need to be seeing. If you have issues with cleans or blanks, more information can be found on some of our YouTube websites where we actually have some processes for cleaning and troubleshooting analytical issues inside the system. So another tip is we just have to look at different types of analytical interferences that may not allow us to reach low-level analysis. So just remember there's two types of analytical interferences for a NDIR, so a non-dispersive infrared detector, which we use in the TOC industry. It's going to be your sulfur-containing compounds in your halides. If you're trying to achieve the most sensitive and most accurate results, you want to eliminate these interferences. Sulfuric acid will form SO3 gas, as we all know. SO3 gas may cause the NDIR to absorb or to give false readings. Then it also could be a damaging factor for that. So we want to make sure that we use an SO3 scrubber if we have some type of sulfuric acid in our sample for preservation or things like that. The halogen scrubber, the U-shaped scrubber, actually comes standard on all the TOC instruments here at Teledyne Tekmar. It's important to be proactive about changing the copper and tin. So if you see these copper and tins start to get discolored or start to brown, we want to swap out and put in new material because we don't want the halides to interfere with our sample analysis, especially if we're going to be working at low levels. So we're going to talk a little bit more now about analytical optimization. So now we know the fusion system can do cleans and how do we get our reagent blanks and what they should be. We're going to talk a little bit more about analytical optimization. So on the screen here, you have is the default TOC pharmaceutical method. The fusion comes with many pre-programmable methods. The default TOC pharmaceutical method is a great starting point for beginning optimization. It's a 9 milliliter method, so that's going to give us the utmost sensitivity. While we look at drinking water or maybe wastewater, those might use 4 to 6 mils because it's not going to be such low level. For us to attain low level, we're going to need a little bit more sample volume, so we're going to start off with 9 mils. 9 milliliters of sample. So method optimization to lessen carryover. So we want to make sure the system is as clean as possible. So how do we do that? So let's start with a method optimization to decrease carryover. The fusion is spec'd at less than 1% carryover for default methods, but we need to consider if your standard or your sample run is over 5 ppm, 1% of that could be right around 50 ppb. So, and if your samples are around 50 ppb of carbon to begin with what we're talking about for this application, then that could cause some issues. So we want to make sure we eliminate the carryover so we can get the best analytical performance out of our system. So what you see here is actually the general tab of the methodology. So what we want to do is we want to go down and turn on the UV reactor rinse. We want to increase our reactor pre-rinse volume to the same volume or more of the sample volume. So we want to make sure that it's at 9 or higher, maybe 10 mils. And this will allow for extra rinses of the UV chamber. So how many numbers of rinses do we want to do? You can set that. And that's going to basically help lessen some of the carryover. But when we go to the Advanced tab, So when we go to the Advanced tab, there's actually a couple more parameters that we can look at or possibly change. Increase needle rinse volume. One thing I generally recommend is that the needle rinse water is the same amount as the method volume. So for this, we also want to do 9 mils. I will typically rinse the same needle with 9 milliliters of DI water or ultra purified water from our reservoir. So that kind of helps us keep things apples to apples. So we're pushing the same amount of sample through and we're cleaning up with the same amount of water to ensure that we're correctly coating the pathway to remove any type of interferences. So one thing that we got to look at too is optimizing basically the calibration curve. So for low level, how do we do something like that? What do we need to do? Well, as analysts, chemists, and have an analytical thinking that we all take, is we need to basically build around our sample matrix. So we got to bracket what we are expecting. So if I'm looking at a 50 ppb, I don't want 50 ppb to be my top end of my calibration curve. I want it to be somewhere right in the middle, so I know I have really good analytical accuracy and precision on that curve. So maybe we'll go from a low level, a 0 or a blank water, to 100 ppb. Now let's say I want to run a 1 ppm is my check for clean in place or for some other validations. Well, I might want to run a 0, a half, a 1, a 2, and a 5, and it's going to put it somewhere right there in the middle of the curve. So we want to bracket our what we are expecting our sample matrix to contain with carbon. So we want to narrow the range. We don't want to be a broad range. We don't want to go from 0 to 10 ppm and try to measure 50 ppb. That's going to push a lot of issues, and we're going to have to take in consideration going through 0, the slope of the line, and different things like that for calculation. So we want to make sure we bracket the curve, and we want to make sure that the value that we're truly looking for is somewhere in that middle of that range, or that we know. Another thing is we don't want to force 0, because if we force 0, it's going to bring down the slope of the line. But one thing we know is there's carbon everywhere. So where the carbon intersects, or where the line intersects on the y-axis, is kind of our background. Is how much carbon we actually have in the background floating around that we know we can back calculate and subtract out. So here's an example of don't force 0, as I was talking about. So some of you might ask, how do we not force 0, or how do we do certain things within our calibration curve, or how do we set it up? Well, we can actually go into our report, click on the open report, go to the interactive tab, and edit the calibration. You know, if you're working in a highly regulated environment where you have 21 CFR capabilities implemented, only certain users could have this permission, or they basically set it this way, or they actually don't run a 0 point. They run a 10 ppb to a 500 ppb calibration, and they don't worry about the DI water point. It really depends on your SOP and how certain things are set up. So once you hit OK, and it goes back and it drops the point. So updating button will be flashing in the software, and it'll basically update this, and here's your new calibration curve that's not forced through 0. So by not forcing it through 0, is we're going to allow for understanding what's in our reagent water, what's in our acid, what's in our persulfate, what's in our persulfate. It's going to allow us to understand what type of contribution the system in the overall reagents, water, chemicals are giving to us, so we can get a good, clear, accurate measurement. Some other things that we need to really focus on here is how do we optimize our sequencing of our samples? How do we do certain things to make sure we're getting the best performance out of the system? Well, we're going to need to run a clean and blank before any samples to ensure the system and reagents is clean enough. If we don't do this and we have a dirty system or high blanks, your results, we're never going to be able to achieve the low level. Also, as I said before, make sure we bracket our samples. Our check standards should not be at the lowest or the highest point of our curve. For this study that we're doing, we actually looked at a 20 ppb check standard on our curve. Our curve was from 0 to 0.5 ppm. And then the carryover up to 1%. So if you run a 5 ppm carbon standard, you're going to get 50 ppb of carryover. So we want to make sure that we reduce that. How do we reduce that? We go back through and do some method optimization, method adjustments, and we can reduce our carryover by including different rinses, larger rinse volumes, and also rinsing out the UV reactor more times than once or twice. We can actually set it to do 3, 4 times different things in the method. So I want to talk about some real world results here. So we went through and kind of discussed what a clean is, what an acid blank is, what a reagent blank is, walking through a little bit of how to set up the calibration curve, how we bracket our samples, how do we do the cleans at the very beginning of our sequence, then we run our reagents, and then we should be getting into our check standards and our samples. So what does that really mean to us? Well, here we're going to look at some results and discussions of this study. So for this study, we ran the default TOC pharmaceutical method. So this comes standard on any system. So we ran a 0 to ensure that our ABSs were low. So we have ultra pure water. And we knew that was going to be less than our 10 ppb point. So as you can see, there is a clear difference, small difference between our 10 ppb and our DI water. The DI water that we use here in our lab is actually from a very good system. So we have ultra pure DI water coming out. So one thing that you'll notice is without the 0 value, and I'll put up a calibration here in a second, the R-squared value should be greater than 3 nines. For this study, we actually got 0.99987, so it's very valid on the curve. All of our check standards pass. So what you see here is we actually ran a check standard at a 20 ppb, 25 ppb, and a 67 ppb. So working down at the low level, some of that we can have a little bit higher precision. A little bit higher precision of the RSD is going to be a little bit higher. It was a little bit higher than what we expected, and we can go through and look at some of the metadata to understand why. But one thing that I've understood in working with some of the scientists globally is that working at that lower level, we're going to have a bigger variance in our RSD, or sample to sample. So that could be acceptable. All depends on your laboratory SOPs. But then we move to our 25 ppb sample and our 67 ppb sample. Our percent RSDs are all less than 5%, which is good, very good. So one thing that we did was, there's always been a little secret or an insider's trick to running ultra low. A lot of times we don't need to run reagent because we don't have that much carbon in there that we need to oxidize. And the reagent just adds to it since we have to subtract it out. So with us running no reagent volume, going back in and kind of doing a little bit of analytical testing, limit curves, we found that sometimes if you're working at that really low level, maybe less than 50 ppb, you don't need to add reagent to the system. And 20 ppb still had a little bit higher RSDs of that 14, but everything else is still falling in line. So there's a couple different things we can contribute that to, is that the variation between rep to rep is a little skewed, but it's falling in line perfectly with the the results that we need. And as I said before, some analysts or some labs will actually allow for a little bit higher variance or higher RSD at that ultra low level compared to a 1 ppm, where a 1 ppm should be less than 5% at all times. So what does that really mean for us? So what's our conclusion? So from this, we want to ensure the system is running perfectly before we start running our sample or considering starting material. So we want to make sure our system is clean, our reagents are ACS grade or if not higher, our DI water or reservoir water is type 2 water or certified less than 50 ppb. Our vials are certified for less than 10 ppb. So those contributing factors, those factors right there, will help ensure a good, clean system to allow us to get to ultra low level analysis. So the default pharmaceutical TOC method meets our LOQ experiment specifications at 25 ppb. One thing that we can look at is to go reagentless. You know, we don't need reagents to run at a low level. But once we start getting above that 100 ppb level, we are going to start needing reagents to be added back in to help with oxidation of the carbon to CO2. So there are some pros and cons about going reagentless. As I said, if you get to a higher level of carbon, it's not going to oxidize. But if you're working down to that 0 to 50 ppb level where water for injection is, you really don't need to add reagents. You can suffice without and provide good analytical accuracy. So from that, these tips and tricks can be applied into many different situations. One, these tips and tricks can be applied to in your analytical troubleshooting. Well, my TC cleans are high. They're staying high. They're not cleaning up. Well, here's a couple places to go look for. Let's change the water. Let's change that. Let's acid wash our glassware. Let's go back in and run a 5% acid as a sample to help ultra clean the system inside along with the other material. So there's different things that we can do there. And then going through and optimizing our methodology is going to allow us to achieve the best results possible by doing extra rinses, by increasing our rinse volume to ensure that we're rinsing with the same amount, if not more, than what sample we're putting through to help clean up that pathway. And then as you can see here, we have really good analytical results at the low level. And then, you know, if we're feeling a little, we want to do more analytical testing, more limit curves and different things like that, we can actually go and continue to go reagentless and work ourselves up to the point of how much reagent do we want to use, so it's not really impacting some analytical results. So with this, in conclusion, a clean system, clean reagents, clean water, the proper schedules, the proper methods will ensure us to have the best detection limits, or sorry, the best limits of quantitation that we can achieve with the fusion system. So with that said, I hope you found this presentation beneficial. I'll be happy to answer any questions. If not, I thank you for your time today. Copies of this webinar can be obtained here shortly. And once again, thank you for your time.